In this video, we're going to use the definition of a directional derivative to see where the gradient comes from. We're going to use two pieces of information. One is our differential, which says that we can approximate the change in f by looking at the partial of x times the change in x plus the partial in y times the change in y. And the second is the definition of the directional derivative, which is our limit definition here. So let's see how this all works out. So our directional derivative in the direction of u, where u is a unit vector, at the point a, b, is given by the limit as h approaches 0, which is going to be an important thing. We're going to be looking at this at an infinitesimally small point, a plus hu1 plus b So let's start off with our definition of the directional derivative. So the derivative of f in the direction of u at AB is given by a limit as h approaches 0. That's going to be an important part of this. F of a plus h times u's I component, b plus u plus h times u's j component, minus f of a b all over h. So it's our old definition derivative from Calc 1, just have some things added to it. So let's see what's going on graphically so that we can get an idea. So first off, let's talk about h. So h is some distance along this unit vector. Let's call this distance right here h. Then what we're going to do is we're going to break this into our components. So let's drop in a horizontal. And here's h. And we'll have some angle in here. Let's call it alpha. And let's get it. So this is our change in y, so our dy. This is our change in x, so our dx. This is that point here, that's our point A comma B. And so let's see how we can get this thing into a form that we can work with. Well, using our right angle trig, dy is going to be h sine alpha. Dx is going to be h cosine alpha. And let's get that into our definition here. So we're still taking the limit as h approaches 0. But now we've rewritten what u1 and u2 are in terms of sine and cosine. So we have f of a plus h cosine alpha, comma, b plus h sine alpha, because those are the components of u1 and u2, minus f of ab, all over h. Now this numerator, we can think of this as equaling a change in f. Well, we just said earlier that a change in f can be approximated by our differential. So let's see what that looks like. Limit as h approaches 0 of f sub x dx plus f sub y dy all over h. Now we'll substitute in our dy and our dx from above. So we have the limit as h approaches 0 of f sub x h cosine alpha plus f sub y h sine alpha all over h. And what's really nice now is our h's cancel out, allowing us to take the limit. So it turns out this is equal to f sub x cosine alpha plus f sub y sine alpha. And what we're going to do is split this into two vectors, which are the dot products. First vector is going to be made up of our partials, f sub x, f sub y. And this is going to be dotted with a vector that is cosine alpha, sine alpha. And notice what we got here. This first part is exactly notice what we got here. This first part is our gradient. The second part is a vector of unit 1. The second part is a unit vector, has a magnitude of 1 and points in the direction that we want to compute the derivative. So this is in the direction of u. So this gives us our simplified way of calculating the directional derivative, which is to dot the gradient with the unit vector. And this leads us to all of our nice properties, because we know that the definition, the geometric definition, means that we're going to look at the magnitude of f times the magnitude of u, which is just 1, times cosine of the angle between them. Now this is the angle between the gradient and u, not the angle from our before. This is just to show this, which tells us, remember, cosine's at a maximum when the angle is 0. So that tells us when u is in the direction of the gradient, it's at maximum rate of change. So that tells us gradient points in the maximum rate of change. And then when cosine is at a 90-degree or pi over 2 angle, this thing is going to be 0, telling us that we have no change in our output when we're perpendicular to the gradient. So this shows us a little bit about where the gradient comes from in this derivation, and also what the normal definition of our directional derivative is without having to use a limit.